very glad to be here. Let me thank Romain, Michon, and all the organizers for putting together the event and for making it a physical event. We're very happy to be here in person. And so we have 10 papers today. We will start with the one which was originally scheduled as the third presentation. And this is a deep HRTF encoding and interpolation, exploring spatial correlations using convolutional neural networks by Divan Zural and co-authors. And this will be given remotely.
A very good morning, everybody. My name is Devansh, and I'm going to be talking about our work on deep HRTF encoding and interpolation by exploring the spatial correlations using CNNs. Before moving on to the problem statement, I wanted to give a quick overview of the data that we are using. So we use the CPIC database for our work. It contains 45 subjects, and for every subject, a total of 1,250 HRIRs were measured at 25 azimuth angles and 50 elevation angles per azimuth angle. We computed the log magnitude HRTFs and then scaled them to a dynamic range of 0 to 1. So the hypothesis is that for every individual, these HRTFs share certain correlations in space. And these correlations are expected to be a function of the body reflections that the HRTFs had undergone. So if we learn these correlations and encode the HRTFs, all the HRTFs into a subdimensional space, then a subdimensional space obtained in such a fashion is likely to be a function of those very specific body reflections. And that subdimensional space is going to encode features that are very specific to every individual. And this subdimensional space can then have several uses. And one such use case is what we show in this work, which is HRTF interpolation from sparse HRTFs. So for the problem statement, we first trained an autoencoder to learn that encoded space from a complete HRTF set. We then used these encoded features to train another network where we fed the network with HRTFs sparsely sampled in space. And we tried to learn a mapping between these sparsely sampled HRTFs to the learned encoded features, and while using the pre-trained decoder of the autoencoder to obtain the complete HRTF. To give a quick overview of the results, first for the autoencoder, but before that, just to give a brief overview of these LST plots. The x-axis in the LST plot is the azimuth angle, the y-axis is the elevation angle, and the color is basically the log spectral distortion of the predicted and the target HRTF at every position. So we tested the autoencoder for two cases, one for a latent size of 6 by 12 and the other for a latent size of 3 by 6. The smaller the latent size, the more the encoding, so the worse the results get. But if we look at these very particular HRTF plots, these are HRTFs at 45-degree azimuth and 45-degree elevation for two subjects. We see that they are quite different looking, but they've both been predicted to a decent degree, showing that the autoencoder has done a good job at encoding very individual features. The next part is the use case of this encoded space. And for this, we again tested for two cases, one for a sparseness of 6 by 12. So there were a total of 72 HRTFs in this one. And then for a sparseness of 3 by 6, so there were a total of 18 HRTFs. So the job was to interpolate from 72 HRTFs to 1250 HRTFs in case one, and from 18 HRTFs to 1250 HRTFs in case two. And we see that we compare our results with bilinear interpolation, and we see that the difference in the results is not very apparent in the 6 by 12 case, but in 3 by 6 case, we see a more clear improvement in our proposed model. And so that being what that means is that's where probably bilinear interpolation fails, when the sparseness increases. Furthermore, our proposed model is also able to achieve extrapolation to some extent, which bilinear model is just fundamentally incapable of doing. There's a lot more to talk about in terms of what the results look like, and also where we are going ahead with this, what is the greater goal of doing what we are doing. But I'll talk about that in the poster session. So I hope to see you all there. Thank you.
Thank you. So the next presentation is about multi-sensor integration design in music for cochlear implant users. The paper is authored by Razan Paisa, Doga Kapdir, Francesco Grani, I guess, Peter Williams, and Stefania Serafin. Ah, no, Ganis, that's correct, okay. There's another one. Francesco Ganis, Peter Williams, and Stefania Serafin.
Hello, good morning. Are my slides coming? Or okay, cool. Test, great, thanks. Good morning. It's nice to see that a lot of you are here this morning. So I'm going to talk a little bit about a workshop that we did, and the title or the goal of our bigger project is how we can use multi-sensor integration to help people with a cochlear implant experience music better. I will start presenting the problem a little bit, and this is a cochlear implant, and I'll just quickly go over what it is. It's this hardware and software system that there's a microphone, there's a processor, there's an interface with the auditory nerve, and the gist of it is that it bypasses the ear completely. So the ear is removed out of the equation in cases where the ear is non-functional. So this presents a lot of challenges and limitations technologically, but also from the electro to brain interaction, which results in music sounding very bad. And very bad does not begin to describe how bad it is. I have some simulations later, so just stop by my poster and I'll show you how a cochlear implant, or several, could sound, if you're curious about that. But the idea is that it's very bad. And these devices are focused on speech, and they work satisfyingly for speech, but not for music. So our goal was to try to remove some of the information that is presented to the ear from the equation and use tactile, vibrotactile stimulation to convey some other information. So we ran a workshop with 3 different types of participants. The most extreme case is when people have cochlear implant in both ears, which was participant 1. The second most extreme case, I guess, would be when you have a cochlear implant and a hearing aid in the other ear, and the third participant had a cochlear implant only in one ear and he was completely deaf on the other ear. He would say that he's not deaf, but his threshold was minus 95 dB. Which is very deaf. All right, and you can also see they have very different experiences with music and how they relate to music. We present them with several installations, and we gave them different tasks. The goal was to let them explore acoustic space and tactile spaces and see what they prefer, what they don't like, and we can conclude about that. This was an installation that was built around the idea that if they could understand stream segregation pre-listening to music, they could focus their attention sort of spatially, but they don't have much spatial information either. So we played multi-track recordings in a quadraphonic setup, so they could literally go and put their face in the speaker, so they can identify, oh, this is a guitar, but it was a piano. It's still better, they could identify the drums, where they come from. And another installation was revolving around seated haptic experiences, and these are just some actuators that we use in some setups. We used some more, and they were allowed to change the amplitude of each and use them in solo mode and combinations and try to see what they prefer. And we played recorded music, but we also played live music. We had drum kit and a bass, double bass, playing through these actuators in different configurations, and it was an ongoing dialogue. I'm going to conclude about I'm going to end the presentation with some conclusions that we got from this workshop. And because of the nature of a cochlear implant and the musical experience of people, the devices have to be very, very flexible to accommodate for everybody's needs. For example, we played jazz, like your standard jazz, classic jazz, let's call it. And one of the participants completely disliked jazz. And he said something along the lines like, yes, these devices, speaking about the actuators, they're nice, but they make something bad worse, because he completely didn't like jazz. So taking into account the user preference and the user's need at the same time, it's very necessary. They kind of emphasized the second point, that the experience should not be degraded. It's already bad, and it's very easy to overstimulate with powerful actuators, so that's probably another key point, that let's make sure that the insurance is not degraded. And it sounds obvious, but it's very easy to do. Another thing that we found out, that in the case of multisensory or multi-actuator setups, it's nice to have control over individual actuators, but also control over the stimulation on individual actuators. So if you play the same stimuli on 2 actuators, maybe it would be a better idea to use 2 stimuli and try to separate them in different actuators. And of course, it's always good that multisensory integration is taking advantages of as many senses as possible. And a good example, one of the participants, who is a festival goer with a cochlear implant, had an epiphany that bass and drums are different. In his understanding, they're always the same. And this was mainly because he could see the drums playing and he could see the bass playing, and he could make the separation in his head. If you have any other questions, or if you'd like to hear a little bit of how this could sound, and just talk to us, we're going to be at the poster outside. And thank you very much for your attention.
Thank you. Okay, next presentation is generating multiple hierarchical segmentations of music sequences using correlative matrices by Paul Lacabette, Corentin Guichoa, and Elaine Chu. Please.
Thank you. Okay, hi everyone. My name is Paul Lacabette, and I'm doing a PhD at IRCAM in Paris. And I'm going to present you a work that I made with Elaine Chu, Corentin Guichoa, and myself. Okay, so what is this work? This work is about music segmentation. So, but first, I will just quickly introduce what is segmentation. So let's say we have a song. We can see the segmentation of this song as verse 1, verse 2, chorus, verse 1, verse 2, chorus. But for the same song, we can also see the segmentation as a verse, chorus, or even at a smaller scale, at, I don't know, measure 1, measure 2, measure 3, measure 1, measure 2, etc., etc. So in this case, we don't have one segmentation, but we have several segmentations, and it's in hierarchical ways. And this is what I want to detect. I don't want to detect only one segmentation, but what I will try to do is to detect several segmentation in hierarchical ways, like this. Okay, so how I will do this? So let's start with a sequence of numbers. So this sequence can be 7, 8, 9, 7, 8, 9, and 7, 8, 9. So usually in the audio domain, researcher works with the self-similarity matrix. So it looks like this. And in the symbolic domain, some people use the correlative matrix. So it's the same idea than the self-similarity matrix, but you increase your number when you are on a diagonal pattern. And this is very useful because you can easily see the length of your repeating pattern. For example, here you can see that the length is 6. And it's because you have a repeating pattern, which is 7, 8, 9, 7, 8, 9, repeated twice. So this is cool, but I don't really like it because you have an overlap. So you can see it. So I proposed almost the same thing. I called it adapted correlative matrix, and I add a condition which without overlapping. So in this case, the longest repeating pattern is 7, 8, 9, and I don't have overlap. Okay, so I will quickly show you the method because I don't have a lot of time. So I start with a musical sequence, which can be a sequence of notes, a sequence of bars, sequence of chord. Then I compute the adapted correlative matrix. Then I design an algorithm to work on this matrix, and in order to have hierarchical segmentations. And what is cool is I can work with several musical sequences, and I can also work with several relations to define my matrix. So for example, if I work with a sequence of notes, I can define several relations on my interval, and it will produce different hierarchical segmentation. I also show you that I can work with a sequence of chords or a sequence of bars. So with a song from the Beatles, I have something like this for a sequence of chord, or for a sequence of bars, I obtain something like this. And in both cases, you can see the three main parts of the songs. And so, just to conclude, why should people care about this work? So if you work on music structures, I think it can be cool. And if you also want to find repetition in a sequence, this tool can be useful. But if not, so I wanted to see if the results were interesting outside of this domain of research. So what I did is I create some videos about hierarchical segmentation with the song, like 20 or 30 seconds length videos. And I put it on a website, which is a bit famous. I put it on TikTok, so just to see. I did it like just a couple of weeks ago. And it was very interesting to see the results. Yeah, because I did like around 20 videos. Up. Okay, I don't know how to. Yeah, I will show you. So it's like, basically I did the same things that I showed you before. And it was very interesting to see that people react to this kind of representation. I have a lot of views. I didn't expect something like this. And it was very successful. And so yeah, thank you for listening to me. And if you want to be TikTok famous, you can just design your own music algorithm. Thank you.
Thank you. Thanks. Okay, next presentation is a differentiable neural network approach to parameter estimation of reverberation by Søren Lister and Cumhur Erkut. Søren will be presenting.
Thank you. My name is Søren Lyster, a master student at Aalborg University in Copenhagen, and this is the paper, A Differential Neural Network Approach to Parameter Estimation of Reverberation. So the concept and the idea came from the concepts of differential digital signal processing and neural networks. I wanted to do some audio differentiation, taking dry and wet audio pairs of impulse responses and using them to tune parameters of a feedback delay network within the neural network. So started implementing a feedback delay network as a plugin. It's an extended version with frequency-dependent attenuation using state variable filters, and it's implemented in C++ using the JUICE framework, where I have all the different parameters exposed. So this is the input-output gains, the filter parameters, etc. So this is just not like a normal commercial reverberation, but this is way too many parameters. But using this, I created a neural network. It has a parameter model that's an encoder, 2D convolutional encoder that takes the input audio and creates spectrograms and uses that to create a vector of parameters that we use in a single layer audio processing model. This model takes the VST3 plugin and uses the parameters and the input audio to generate some output audio, a red signal that can then be used in audio differentiation using the multiscale spectral loss. The audio processing layer is where it gets a bit fun. This is a custom neural network layer that uses the pedal board. It's a library by Spotify's Audio Intelligence Lab. And it can host BC3 plugins within Python, so you have a lot of control, and you can use it in different Python environments, including machine learning and deep learning. And then, of course, we had to implement a custom gradient implementation so we can calculate the gradients for all the different parameters. I did some evaluation with two different tests where we have, again, these impulse-like snaps we used as dry signals, and then we created a wet signal as our impulse response as our target audio. And we can see for both projects that the parameters tuned, like they're approaching the correct parameters to create some perceptual correct impulse responses, but it's not still not there, but we're approaching it. And we could see we had reduced models as well, where we had just one delay line configurations of the FDN plugin, and it performs very well there. It's easy for it to calculate or estimate all the different parameters. And with 4 delay lines, it gets more complex, and with these test results for 16 delay lines, it gets exponentially complex. As part of my master thesis, I've been doing a lot of extended work with this. We've updated the FDN implementation, added more stuff to it, changed the filter implementation completely, added parameterization for delay line lengths and so on, and introduced some new novel loss functions with looking at more perceptual qualities of reverberation. And then I've done some perceptual evaluation. But all of this has been done in the last couple of months, so come by my poster if you want to talk, and thank you for your attention.
Thank you. Okay, we can move on to the next presentation, which is Style Wave GAN. Style-based synthesis of drum sounds with extensive controls using generative adversarial networks by Antoine Lavaux, Axel Robel, and Mathieu Berry.
Good morning. I'm Antoine Lavaux, engineer at Apera Technology and PhD student at ERCAM. With the slide, it's always better. Somehow. Great. Technical difficulties.
No, but that's not the problem. It's hiding the menu. Like to actually change. It's to like pin it.
Bon, restons-en là. Ouais, je crois que. Yeah, it will work. So, drum synthesis. Why do we use neural networks? Well, if we have drum synthesis, we want quantity, quality, and simplicity. Good luck to have all three at the same time. Here comes the neural networks, and especially the GANs. A GAN, generative adversarial network. A generator which takes noise as its input and make fake data as its output. On the other hand, a discriminator, which will take real and fake data and output the probability of said data to be real or fake. Style GAN, an evolution of the vanilla GAN, where instead of using directly the noise of the input, said noise is transformed into an intermediary representation called style. This style will control each layer of a synthesis generator, as seen on the right. And WaveGAN, well, it's just StyleGAN originally is an image generating network. By flattening everything inside, we get a waveform generating network. Well, it doesn't answer the control part, so we introduce a modification of the audio commands features where we re-implemented them to be compatible with the automatic differentiation network, framework of TensorFlow. Does it work? Let's see. At least it hasn't been done before, so yeah, it's novel. So first, sound quality compared to Neurodrum of WaveGAN, we get a way better FAD, fresh air audio distance, lower is better. So we go from Neurodrum with 25, WaveGAN 11, and finally Style WaveGAN with 4, which is okay. Perceptual test on an upcoming paper show it's quite good and better than DrumGAN 2. About descriptors. Yes, it works, even though it's a bit cut on the screen. All these little, first, the red vertical lines. They represent the values of on the dataset for different descriptors. Here, brightness, warmth, and depth. The little black dots are the, well, error bars of Style WaveGAN with given input. And the little blue crosses are Neurodrum. So Style WaveGAN is, well, quite linear and can generalize outside of the learned values, which is great. In terms of more quantitative metrics, we have on the first table a comparison between Neurodrum, DrumGAN, and Style WaveGAN. We get almost perfect accuracy. Higher is better on the table on the upper side. The other part is just describing a new metric we introduced in the paper, which is basically the mean absolute error on a certain set of values. And we can see we achieve a very small error, especially compared to Neurodrum. And another coming paper will show it's imperceptible, which is quite great news. Well, that's a good conclusion. It makes noises, everybody's happy.
Thank you. Okay, next presentation is a web platform to extract and investigate music genre labels in Spotify by Adriano Barate and Luca Andrea Ludovico. And the presentation will be given by Luca. No. Oh, cool. Well, almost.
I'll try this way. Good morning, I'm Luca Andrea Ludovico from the Laboratory of Music Informatics of the University of Milan, and my presentation deals with a web platform to extract and investigate music genre labels in Spotify. The project deals, the title of the project is Music Genres in the Spotify Era, Social Construction, Computational Fruition, and Productive Distributive Practices. The short name is SpotiGem, and this is a multidisciplinary project funded by the University of Milan and involving not only computer science experts but also sociological and musicological skills. And the idea was to investigate the transformation of the concept of music genre operated by digital streaming services. The focus is, needless to say, is on Spotify, and the result was, from the point of view of computer science, the result was the design, implementation, and public release of a web platform called SMC-22 Hub. I will give a demonstration of this platform, web platform, during the poster presentation. This is the link. Well, concerning Spotify API, the idea is that Spotify can return via web API calls a number of audio features concerning user pieces. And in particular, Spotify extracts score aspects, such as time signature, key, mode. It returns the mode of the piece concerning danceability, valence, energy, and tempo, and tries to extract also the physical properties, such as the loudness, the speechiness, and the instrumentalness, and also some context information, such as liveness and acousticness. The problem is that audio features extracted by the API in general should be somehow self-descriptive, but they are not completely documented. For instance, in many cases, the values extracted are ranges between 0 and 1, but what does it mean, danceability set to 1, for instance? What are the scales of these values? What are the distributions of values? What are the algorithms used to extract such information? So, what we have developed is SMC-22 Hub, namely a publicly available web platform that has been organized mainly into 3 views. The first view is the user view. This is an example, where you can explore via the web, you can explore some metadata about single users, and above all, the list of personal and featured playlists. The second view is the playlist view, focusing, of course, on single playlists. So here you have the list of pieces for each playlist and the possibility to open the audio features. So the next slide will show the piece details. Here you can see a list of the audio features returned by the API. Let's go back to the playlist view. We have also 2 buttons with the possibility to download this list of values in terms of comma-separated values, which was particularly important for the automatic analysis and comparison of results required by the other components of our project, required by musicologists and experts in sociology, and also the possibility to go to charts, to have a graphical representation of values. I will come back to this subject later. The third part is the album view, focusing, of course, on single albums and the possibility to see the list of pieces and their values. So, concerning charts, here I have listed a number of examples. For instance, this is the genre distribution of a single playlist. In this case, we have not removed single genres. They could be removed by clicking this part of the interface. This is a chart concerning the valence of a specific playlist. And there is also the possibility to compare these charts, this set of values, with other playlists. For instance, inserting a playlist ID here. Here you can see an example of comparison between playlists, focusing on the energy distribution of 2 of my personal playlists, my summer compilation in 2020 and my summer compilation 2021. So you can see a big difference in energy distribution. Maybe the mood, I don't know. Anyway, the project results obtained so far have been published or are going to be published. Gandini and Corbella are our colleagues at the University of Milan from sociology and musicology. And they've used our tool, our web tool, as a support tool to extract information and conduct their kind of investigation. So, thank you for your attention, and I hope to see you at my poster to have a live presentation. Thank you.
Thank you, Luca. Next presentation, semi-supervised convolutive non-negative matrix factorization for automatic music transcription by Horan Wu, Axel Marmoret, and Jeremy Cohen. Ah, you made it. Okay.
Yep. It's my main contribution to the conference is setting the slides correctly. Okay. So, yeah, as it was mentioned, it's a joint work with Horan Wu, who was an intern for 2 months in our team, and Axel, who is a PhD student right here presenting tomorrow as well. And I'll be talking about what is called automatic transcription. I think it's been discussed in the previous days, but just as a quick reminder, suppose you start from a recording of some audio file of a music piece, and you are interested in producing the music score that has generated this audio file. And the way we do that using non-negative matrix factorization is you take the audio excerpt, you compute, for instance, its spectrogram, it's a matrix, a non-negative matrix element-wise, and you would try to search into this matrix for the frequency patterns of each note that is played and the time activations for each note. So if you get to this point, then you can imagine that we can like threshold the activations on the right and recover like when each note is played. Supposing we're able also to know which note corresponds to each template extracted, because this is fully unsupervised, right? So what can AMT be used for? There are several use cases, of course. 3 of them here are educational purposes. So if you're a student, you're playing, and you want feedback on how well you tracked the music sheets, well, this can help you. This is very helpful, I guess, for musicology analysis, where you want to extract deep information on the music, but you only have the audio and not symbolic data. And I think it's also a great tool if it was fully working for digital audio workstations as a plugin. Okay, so to get more into details, how does the naive, blind, non-negative matrix factorization technique works? So basically you write an optimization problem. Here I'm minimizing the Kullback-Leibler divergence between the data Y, which is my spectrogram, and 2 matrices W and H, which are element-wise non-negative, and these matrices, W contains, in principle, it should contain for each column like a spectral signature for each note that is played. For instance, with the piano, you would need like 88 of those, basically. And the H matrix, as I showed earlier, contains all those times activations on each row. And when everything works perfectly, like here I give a very naive example on the 5 first second of jazz standard called Jordu, which is like 1 note playing at a time. It's like da-da-da-da-da-da-da, so it's just 1 note. And then NMF has no issue, right? It's just finding every single note, every single activations. It's perfect, but there's a catch. It doesn't actually work on proper like audio. So if you take the next 25 seconds of the same song, that starts to have some polyphony, several pitches happening at the same time. And well, the W matrix looks kind of okay. Like you can see some pitches, some like localized frequencies, but H matrix sometimes has very, very noisy rows, and you can see a lot of spurious activations. And well, I guess it's only fair, like it's a fully unsupervised method without any information. It doesn't work out of the box. So there's been a long history of improvements over this technique. I've listed some of them here, and I guess the most prominent line of work nowadays is to completely drop NMF and just work on the fully supervised deep neural networks. We've seen some talks discussed a bit of those methods. But I wanted to go further into the direction of unsupervised or at least semi-supervised methods. And what I mean by semi-supervised is the only information I want to use which is labeled is I'm able to record or have some information on the spectral templates for each note of my instrument. So imagine you have the piano that's used for the recording. I'm going to use every single note, record audio for every single note, and that's going to give me some templates. It's a bit less data than 1,000 hours of piano recordings on this clavier or something. There's been many works in the domain. What I'm proposing in this talk will not be so much new, but it's more like aggregation of several ideas together in something that I think is working quite well. Okay, yeah, and I'll be focusing especially on one kind of improvements of naive NMF, which is time-dependent templates. So templates will have time dependency, not just frequency dependency, and I have to speed up, right? So in a nutshell, what we do is, as I said, we take signal nodes, we record them, gives us template, and we have a training phase where we learn the templates, and then we only have to do the activations, and we use not NMF, but a convolutional version of that, where you don't just outer product W and H, but you place the templates in the data. And well, you can see on the poster, because the results here are impossible to read, but it's working similarly to some fully supervised neural networks, so that's good, but it's time consuming and it doesn't generalize well. Okay, and feel free to visit. Thank you.
Thank you. Okay, let's move on to next presentation. Defending a music recommender against hubness-based adversarial attacks by Katharina Prinz, Arthur Flexer, and Gerhard Widmer.
Thank you. Okay, perfect. Hi everybody, my name is Katharina Hutz, and today I'm going to present to you joint work that I did together with Arthur Flexer and Gerhard Widmer from the Johannes Kepler University in Linz. The title of our work is Defending a Music Recommender Against Hubness-Based Adversarial Attacks. Okay, let me first give you some context. In our work, we look at a real-world music recommender system, namely the FM4 Sound Park. This recommender presents you for every current song that you're listening to with 5 most similar songs, which you might be interested in hearing next. The recommendation system is content-based, meaning that every audio file is represented as a point in the latent space of the music recommender. The most similar songs are then found simply by looking for the nearest neighbors within this latent representation space. If you listen to another song within the catalog of the music recommender, then you will of course get 5 new recommendations. And if you listen to another one, you will get 5 more recommendations, and so on. And if we repeat this process and collect a lot of recommendations, then we will actually find something that is the direct result of the so-called hubness problem. Hubness describes the issue in high-dimensional spaces where some points lie very, very close to a lot of other points, while the remaining don't. So in this particular application, this means the point in the middle here, indicated by the different color, is a close neighbor of a lot of other songs and will be recommended very, very frequently, a lot more frequently than the remaining songs maybe in this catalog. Some songs might even never be recommended at all. In previous work, we sort of exploited this issue and tried to add a new song into the catalog of this music recommender with an artificially high amount of times that this specific song is recommended. So what we basically did is we tried to change the latent representation of this song that we added and pushed it towards the representation of a hub song, meaning a song that was recommended frequently already. And at the same time, we tried to leave the sound of the original song unchanged, or at least as close as possible to the original. This is less than ideal if you think about it, because while it's really nice for you if you manage to increase your recommendations artificially, you will end up reducing the number of times that other songs are recommended. You might even push out some of the songs of the recommendations in total. So of course we want to defend against this, right? This is what we did in this work. We tried to investigate different methods how we could defend against this kind of attacks. And what we ended up doing is we tried to reduce the issue and the effects of hubness themselves. So we looked at a method to do so, namely mutual proximity, which has been introduced previously. And mutual proximity is a method to reduce the effects on hapness by repairing asymmetric neighborhood relations. If you think back to the example that I just told you about, so the song in the middle is the nearest neighbor of a lot of songs and is recommended very frequently, but all of its neighbors won't be within like the 5 nearest neighbors to be recommended, so they aren't the nearest neighbors in return. And mutual proximity is a method that fixes this issue. Instead of only applying mutual proximity to the music recommendation system, we also tested the boundaries of this way of defending by attacking the defended system. We even included some knowledge about the defense within our attacks and looked how well this works. And if you want to know how well it works, then please visit me at my poster. I'm glad to answer any kind of questions. Thanks.
Thank you. Okay, next presentation, Audio Metaphor 2.0, an improved classification and segmentation pipeline for generative sound design systems by Joshua Kranabetter, Craig Carpenter, Renaud Bouguin-Chemeb, Philippe Pasquier, and Miles Torgood.
Thank you. Hello, everybody. I'm Josh Kranabetter with the Spiral Lab at UBC, and we're in collaboration with the Meta Creation Lab at SFU. And this is Audio Metaphor 2.0, an improved classification and segmentation pipeline for generative sound design systems. So Audio Metaphor 2.0 is the second iteration of the OM project. It's an automatic soundscape generation system that transforms input text expressions into a soundscape composition. With the live query and composition system, you can enter a query like a quiet walk in the forest. Then you can set a duration for it, set curves for valence and arousal, which you can think of as pleasantness and eventfulness. Then you can render the soundscape and you can play it or download it. Now, improvements in Audio Metaphor 2.0 are a vastly expanded audio corpus, an expanded feature set, increased accuracy in emotion prediction, and improved segmentation. And if you want to talk about the rest of the pipeline, you can come see me at the booth after. Now, a little bit of background. R. Murray Schafer popularized the term soundscape, and he defined it in a few ways. All the sound from a particular environment that reaches the human ear, and he called it the music of the environment. Now, in soundscape composition is the creative practice of processing and combining sounds to evoke associations, memories, and imagination within a listener. Now, soundscapes are rich and complex, so to compose them, we need a corpus of audio with enough depth and variation to meet these challenges. Now, our Freesound Corpus comes from Freesound, which is a collaborative repository of over 500,000 sounds and associated textual tags. And on the plot here, you can see the size of the number of audio files in the OM original versus OM 2.0. So for audio files, we go from about 4,000 to almost 400,000. And in unique tags, we go from 9,000 to about 92,000. To compose soundscapes, we first need to describe the sound file computationally. We switch from the faster Yaffe feature extractor to Essentia in favor of the plethora of features it offers. Okay, so now we can use our high-level features to make some high-level predictions. We evaluate the emotion of segments using Russell's circumplex model of affect. We predict valence and arousal using a random forest regression model. Our arousal model comes in at about 92% accuracy, which is the current state of the art. Our valence model comes in at about 72% accuracy, which leads us to by about 3% to 2018's deep learning method, but is still about 10% better than the OM original. This data is used to arrange segments according to the red and blue user-specified curves you saw earlier. So soundscape designers and sound designers use or manually segment audio files for use in composition. We use a ridge regression model to automatically segment these files into background, foreground, and background with foreground. And as you can see in the plot here, the results are relatively the same as the last version of Audio Metaphor. In segmentation, we join like classes and use a k-means filtering algorithm to remove the noise of misclassified segments and negligible class appearances between segments of the same class. Now, we perform all these predictions only once, and we store the results in the OHM database. So we'll have textual tags, valence and arousal levels, and a background-foreground class. And we use all these segments for use in composition. Now, to sum it up, the new version of Audio Metaphor takes steps to improve generative soundscape composition by vastly expanding the database, improving emotion prediction, and improving smoothness and segmentation. Now let's take a listen to a few samples before we go here. So we'll listen to a submarine filling up with bees and magical, windy, reverberant chimes. And you can try Audio Metaphor yourself by scanning the QR code and come say hi at the booth. Thank you. Thanks.
Bonjour à tous, ici Charles de l'agence Gros, j'espère que vous allez bien. Aujourd'hui, on parle des différents forfaits, leurs avantages, comment ça fonctionne au niveau de la facturation pour Monday. Donc, actuellement, je suis dans le monde.
Beautiful Canadian accent, actually.
Okay, so we're at the last presentation, which is about scream detection in heavy metal music by Vedant Kalbag and Alexander Lerch.
Hey everyone, so I'm Vedant. I'm from the Music Informatics group in Georgia Tech, and I'm here to present scream detection in heavy metal. So a lot of work that's been done with scream detection was actually, so some great work that I used as the idea for this was unsupervised clustering for heavy metal. And one thing that I noticed was missing from this was that there was no clear way to distinguish between the different classes that were formed. So in this work, I actually present a data set of manually annotated screams with the start and stop times, along with the different type of screams that's present. So let me go back, rewind a little bit. So I'm sure all of you know that heavy metal vocals are very different to basically everything else you guys are familiar with. And there's a whole bunch of techniques that are used that people colloquially refer to as screams or growls. Now these are made and these effects are modified by changing the length and shape of your vocal tract. And there are three main types of screams that are commonly used in metal today. And to anybody here that doesn't like metal, I apologize, because I'm about to play some audio samples. So I'm going to show you guys the three main kinds that I was talking about. And if you guys want more, please do drop by my poster. So this is a high fry scream. So that's an example of a high fry scream, right at the end there, where it's go like that. I'm going to show you a low and a mid now. So the lows are like really low. You can tell. So that's a low fry scream, very common in a lot of the deathcore and metalcore subgenres. And this is a mid fry, which is most common. Broken the paradigm, an example must be set. Okay, back to the presentation now. Where is that gone? Okay, there we are. So those were the samples. So coming to the data set that I created, it consists of 57 songs with a mean duration of about 300 seconds across 34 bands and 47 albums. The total data set duration is almost 300 minutes. So there's quite a lot of audio that I had to go through to annotate this stuff. It's annotated into 5 labels: clean or singing, low fry scream, mid fry scream, high fry scream, the ones that I just showed you, as well as layered vocals, which contain combinations of 2 or more of any of these effects. I did include genres such as death metal, groove metal, progressive metal, that's a typo, black metal and metalcore, in an attempt to include both old and new subgenres of metal, as well as to include a wide variety of the vocal styles that are present in metal. So let's talk about the classification, because I also present a baseline system for classifying these vocals based on my data set. Before we get into the actual features that I used, I did divide this, each of these files into 2-second blocks with a 1-second hop. And I did use the splitter algorithm to extract the vocals with interesting results. So I conducted 5 different experiments with different feature sets. I used MFCCs, delta MFCCs, spectral features such as contrast, centroid, flatness, and roll-off, as well as temporal features such as RMS and zero crossing rate. I did also use the VGGH embeddings, which actually seemed to work pretty well for me. Additionally, I also used a log meld spectrogram along with the CNN. So up here you see the class-wise spectrogram, and you can actually see some very interesting patterns formed, especially with the singing. You can see there's some clear harmonic content that you can see with all these horizontal lines. The screams, the high screams, you can actually see a very distributed, noisy signal almost. As much as that hurts to say it, it looks like noise. The mid-fry screams and the low-fry screams do have similar patterns, but in different, the energy distribution is slightly different. And actually, this brings me to my results. So I conducted 2 experiments, one with a 3-class classification and one with a 6. And the 3-class classification, actually the CNN worked best with the log meld spectrogram, and I got an F1 score of 87%. There was a significant improvement over the SVM with all the different feature sets that I used. However, when I used the 6-class problem to classify basically into all of the different annotations that I have in my data set, the SVM actually outperformed the CNN, which was quite interesting. And please do come by my poster and we can discuss why this happened and more. Thank you.
Thank you. So this concludes the presentations. Please join the presenters at the posters and enjoy the rest of the session. But first, a message.
There we go. Thank you, Federico. Before you guys go to the posters, there are a couple of things that I just want to tell you about, which are important. So the first one is about the program of the conference. So if you go on the conference website,